Can hear you now.
Okay, perfect.
Okay, so Eileen said she'd be a bit late. We'll go ahead and get started. Okay, before we do, does anyone have any questions? No questions? Okay. All right, well, today we're going to talk about testing. So let's start this with a little toy function that we've used before. So here's our motivation. We have this function called add. And my question is, does it work?
Depends on the inputs.
Good. Is it correct, and how can we prove it? So it depends on the inputs. Like if we do this, that looks like it should work, right? It should work as well, even though we have a float and an integer. What happens if we do that? Yeah, it raises a type error. Same thing here. Okay, so when we think about testing and monitoring the behavior of our codes, I like to use an analogy, and I call these code planes. So imagine this blue plane is flat, and that's going to be our desired behavior, okay? Our actual behavior, though, might be a function more like this. And so what we do when we're testing is we're essentially measuring the distance between our desired behavior and the actual behavior. And if that distance exceeds some tolerance, the test fails. In some case, there's no tolerance. Integer addition should be exact, but float addition might be off by just a little bit, right? Okay, so looking at testing taxonomies, I'm going to refer to several domains, and the domains refer to what the planes actually mean. And then several approaches, and the approaches are how we sample the domain and measure the residuals. So for the domains, we have compilation. That basically just means, does your code compile? And if so, you've already eliminated a certain class of bugs that, or a certain class of programs that wouldn't compile at all. So with Python, we have kind of a trade-off in that the compiler doesn't do as much checking as, say, a C compiler or the Rust compiler, but we do have a more flexible language. So that's a trade-off we make in language design. The next level would be unit testing. And typically this just means that we're testing one small function or class. It's kind of ambiguous what a unit is exactly, but we're going to call it kind of one unit of code. And we have integration tests. An integration test, as it sounds, it will string together several units. And then the last type of test domain would be end-to-end. You might be testing what a user would experience as they interact with the software. So for the approaches, we have an example-based approach where we're simply going to define a set of inputs and desired outputs. There's also a property-based approach where rather than define a specific input, we might define a whole class of inputs. Say for all floats, we should have this property of our function. I'll show you more of that in a second. There's also a testing approach called mutation testing. And how this works is we actually change our code and then we expect our test to fail. So it's a way of testing whether our tests actually cover enough of our desired behavior. And then finally, there is mathematical tests. And this basically applies to functional languages like we talked about last week, where we have guarantees that the abstractions in our language behave in certain mathematical ways. And if they do, then we can just use formal mathematics to reason about our program and prove that it's correct. And that sounds nice. It's actually quite difficult to do in practice. I don't have any experience with it, but that's what I hear. All right, and the other thing to consider is the level of automation. So do you have to do this? Do you have to like click through a bunch of examples to get your test to run, or can they just run automatically? And of course, automatic testing is better, but I think there are some cases when just having a human in the loop is a lot more efficient. And you wouldn't run those tests as often, but for example, if you were building a code that did a lot of visualizations, it's hard to get the computer to determine if they look right or if they look nice. So you might just have it generate all of its visualizations and then just check that they're all reasonable once before you do a release, something like that. Okay, so here's the domains. We talked about this earlier. We have the compiler that's going to catch a lot of potentially invalid programs. And then we have our unit test, integration, and end-to-end tests. But as we move up this pyramid, it's important to know that your cost, how much time it takes to run the test, as well as the coverage of your code, how many bits of your code the test is going to affect, and then the complexity of the test all increase as we move up. So for that reason, usually it's drawn as a pyramid because you want to have more unit tests and integration tests, for example. That's not always the case, but that's kind of the traditional view. All right, so let's look at some examples of testing domains. This is a unit test that I took from scikit-learn's test suite. So what they're doing here is they're saying that a certain error message should happen if there's a sparse array passed to one of the regressors. And so in this part, they're setting up the test. And then down here, they're actually checking if the test is raising the error that they're expecting. Okay, so that's a good example of a unit test. An integration test might be looking at scikit-learn's pipeline function, where we string together several transformers, regressors, whatever else we're going to put in the pipeline. And so in this case, we're testing the ANOVA and the logistic regression together, and essentially just checking that they work together. And here's an example end-to-end test from DASCore, one of the libraries that some of us here are working on. So basically, we go through the entire user's interaction with the code. They might start by loading some data. They're going to do some filtering, some visualization, and then save some data out. So just making sure each one of those steps works is the idea behind this test. Now, we might add some more asserts rather than just making sure that it doesn't raise an exception, but this just kind of demonstrates the idea. Okay, so let's talk about some of the approaches now. The example-based, like I said, we just pick one example for an input, and then we have a known output, and we can do this any number of times. We just want to make sure that the behavior matches at that point. And then once we find an input that breaks our code, it's a good practice to keep that as part of the test suite. So in future versions of your code, test that input that broke your code before, just to make sure that you don't get that same bug coming back. The problem here, though, is how do we know when we picked enough examples? And if we look at one of our tests that we could write for our add function, here we have 3 examples. And that gives me confidence that it works in these 3 cases, but it doesn't give me confidence that it works or the behavior is even well-defined for all the cases. We saw some cases for which it wasn't. So looking at our code behavior plane, we pick some examples which represent these blue dots. And then we might fix our behavior where those dots measure some divergence from the desired behavior or the actual behavior. But we could still have a code plane that looks like this, where we have clearly poorly performing code in areas that we just haven't tested yet. All right, any questions about that? Is this analogy clear? Okay. Okay, so if we move on to property-based testing, the idea here is to generate many examples or a distribution that covers, for example, a distribution of floats greater than 1. We could do something like that. And then what will happen is we want to keep track of our failures. So if we run the test suite, we find out that one of the numbers causes it to fail. Then we want to remember that number and run it next time to make sure the bugs have been fixed. Otherwise, it's kind of like playing whack-a-mole. If these are just purely random, you might have a failure and then you have no idea how to reproduce it, right? So this is important. When you do this, it's important to put emphasis on edge cases. So looking at 0, -1, nan, infinity, that sort of thing. These kind of exceptional values for certain class of inputs. And this, of course, is going to be much more expensive because instead of just testing 1 point, we're testing many points. And as I mentioned, it can be non-deterministic. There's ways to get around this, like storing the values that have failed the test, but it can still be a problem for reproducibility at times. Okay, so here's an example of a property-based test for our add. What we're doing here is using the framework hypothesis, which is a Python framework for doing this. And so we have our function add, and then we're going to add a decorator to our test function here that says, given that our first parameter f1 is going to be some value of floats, and f2 is going to be some value of floats, or some distribution of floats rather, then it's going to run this test many, many times, substituting in the values that it comes up with here. Okay, does that make sense?
So it's going to generate different floats automatically.
Yeah, it's going to generate a whole distribution, and it's nasty because it will choose the values that are most likely to break your code. Like I said, the infinity, the nan, and so on. There's ways you can restrict it to a certain subdomain, but this is kind of the simplest example. And so we get something maybe that looks like this. We can test a whole line of our code plane, but there's still areas for which the code might be diverging from our desired behavior that we haven't measured with this sort of test. Okay, so who knows who this is? What is this? Anyone else grow up in the 90s? Wilson, did you watch TV and
This show.
not this show? Okay. Okay, so this is a Sentinel from X-Men. What does the Sentinel do? It's to fight the mutants. It kills the mutants, right? And there's these giant robots. So with mutation testing, it's a similar idea. What we're going to do is mutate our actual code, and we'll make syntactically valid changes to the code. I'll show you an example in a second. So it has to still compile. If it doesn't compile, this is worthless. And then we're going to run the test suite. And if we get the test suite to fail, that means we've essentially killed the mutant. We found the mutant variant of our code and our test suite caught it. If it doesn't, it means that we failed the mutation test. And here's an example. So here's our original function, add, and we have our test here. Now, if we were to perform a mutation test, what we might do is change it to this. So now add, instead of adding these two things, it's subtracting them. And we would hope that our test suite, when we run it under this new mutant variant, would fail. Otherwise, we're not doing a very good job testing add if subtract passes our test. Yeah. So I like to think of it as kind of fuzzing or adding noise to your code plane and then seeing if you can pick up that noise at different levels. That's how I conceptualize that. Okay, the last one, as I mentioned before, mathematical type tests. These are more difficult, but pure functional languages, you can actually prove them correct via mathematical proofs. And of course, this assumes that your compiler is correct and that no cosmic rays flip bits in your machine or something. You know, nothing extraordinary is happening in your computer like that. But the problem with these is then someone has to prove that the proof is correct, and then the proof of the proof, you know, so we get into more formal mathematics and it can be difficult to automate, to say the least. All right, so that, I'm going to give some practical advice on writing tests now, but before I do, any questions on the approaches or the domains? Just for your information, like mutation testing and property-based testing. Property-based testing is more common than mutation testing, but mutation testing is like you have really important code. Maybe it's like flying an airplane or something. That's the level of testing you'd probably go to. For scientific codes, I'm not aware of any libraries that are doing mutation testing for more than just like toy examples. Okay. All right, so when and how to test your programs. The law of diminishing returns applies here. So if you do a little bit of testing, I think that can greatly improve the quality of your code. But if you spend a ton of time testing, it's starting to not improve the quality all that much. And so selecting the right level of testing. So how we test, say, a script that you're only going to run a couple of times versus a library that thousands of people are using are very, very different. So some questions to ask when you're trying to decide how to test your software. How long is the software going to be in use? Is it one time and one and done? And you probably don't even worry about testing, just run it and make sure the outputs look right. How many people are going to interact with the software? Again, is this just for you, or is it something that could grow into a larger project? What are the consequences of failure if we're writing the autopilot for an airplane versus a script to reformat some file names? Very different cost of failure. And how many lines of code or how many files could this grow into? If it's a small project, testing is less important, but as it gets larger and larger, it becomes more and more important to kind of hold it together and to manage some of the complexity. So looking at, say, a research code that you're writing for your research, right? How would you approach testing for that? Or how do you approach testing? What do you think, Werner? How do you do testing? Or do you do formal testing, or you just sort of run it and it looks right? How do you test research code?
I get an expected result. That makes sense. But sometimes there are some certain people to make sure that this sort of helps not only to test but also document the goals.
Right.
So when I see it again,
Yeah. Yeah, so that's something that I didn't mention yet, but putting assert statements in your code is a way to kind of test it as it runs to make sure that everything you assume about the state of your program is correct. Yeah, good.
I just usually verify the code by another example that I don't use by another data set or something that, for example, I see in the paper the data is available. So I just verify that.
Yeah. So what kind of test would you consider that to be in our domains and our approaches? Should I go back to him? All the way back. Okay. Yeah, I would agree. Yeah, and it's probably example based, right? You're picking one example from a paper. Okay, good. Yeah, I think that's really common. That's how I do a lot of my research code as well. I'll typically reach for a formal testing framework when I'm writing something that I know other people are going to use. If I'm just using it, I'll probably write some certs in there for sure. And then I might have some small tests like at the bottom. I'll show you how that works in a second. But yeah, so when people first learn about testing, I bring this up because a lot of people tend to go overboard. You know, you're going to start testing every little tiny thing. And it can be a really big waste of time depending on what your code is. And if you don't ask yourself these questions first, yeah, you might be wasting time. Conversely, though, if you don't ask yourself these questions, you might not be testing something, and then it might become unmaintainable and just a huge mess and waste a lot of time that way, because if you had written the test originally, you're saving time down the road. Okay. So a few ways to test. We talked about this running a few end-to-end tests. Does it generate the figures? Does it look right? Does it match an analytical solution, for example? We can write targeted unit tests. Maybe there's a really difficult part in your code. And so rather than doing a full end-to-end test, we just want to make sure that one little bit is working correctly. We can also include some of these tests in the same file so they can live really close to the code. But if we're building a library or utility that other people are going to use, I think using a testing framework is really the right approach. So let's look at a few examples here. We have a single test file. Our add function again here, although this should be plus, this is still mutated. So what we might do is have this test, and then at the bottom of the file, we have if dunder name equals main. And we talked about that a few weeks ago, I think. Does anyone remember what this does?
It kind of checks if you default. I mean, you have this and you do Python, this script. It's gonna check if the his name is gonna be replaced by the name of descriptive argument.
Yep.
Like if this is the case, then run this test.
Right. Yep. So the idea here is if you run this with Python space this file name, dunder name is going to be equal to main. So this bit will run. But if there's another function in or another module that's importing it, it's going to be the name of the module here. So this won't run. So that might be a way you structure your research code. For example, you have utilities, you have all the tests there, and then the utilities get imported by another script. Then when you want to run the tests, you just run the utilities as a script. When you want to import from it, you just import from it. Okay, so now we're going to get into the PyTest framework, and I'm stalling a little bit here on purpose because Eileen said she'd be about 20 minutes, and I think she wanted to see the PyTest stuff, but we'll go slow here. So PyTest is the de facto Python testing framework. There's really only two choices when you're writing tests in a framework type setting for Python. It would be PyTest or unit test. And the reason you choose unit test is it's built into the standard library. So if you can't have any dependencies, for example, then you might use unit test. That's what the Python test suite itself is written in. But otherwise, PyTest is usually used. It's really highly extensible, so you can change how it discovers tests, how it runs tests, how it reports failures, all sorts of things. There's over 100 different plugins to modify its behavior that you can find on PyPI. And what's important here is that it separates the testing setup, the test component, and the teardown. And we'll talk about the anatomy of a test in a few slides, but it lets you kind of separate these concerns so they can be more usable. And then you can configure it with all sorts of command line arguments. You can add your own command line arguments. You can control which tests get skipped under which situations and so on. So it's very powerful, very configurable. So how to use PyTest? We'll look at a few examples in a minute, but basically what we do is we call PyTest from the command line. So we just open the terminal, type PyTest, and then it's going to do a few things. It's going to parse all the command line arguments that we pass to it. It's going to discover all the tests, and how it discovers tests is it looks for files that start with test and then whatever else. So if the file starts with test, it'll just look in there for test cases. It's going to collect all the tests and fixtures and the testing files that it finds. So what it does to discover if something represents a test is if a class starts with test and then anything else, or functions or methods that start with tests, it's going to assume that those are tests. And then it's going to figure out which tests depend on each other, or rather which tests have fixture dependencies, build a graph that resolves all these dependencies, and then run it in a sensible order. And you can sub-select certain tests, so it'll skip some, run others, depending on what you've told it to do. Okay, so this can be a bit confusing at first because this is a framework that you give your code to and then it runs your code. It's not like a library where you can see the control flow of how you're using NumPy or SciPy, for example. So for example, here, we're going to just call PyTest, and let's assume we have this test add function, and then it's just going to run that file. We're not going to see how it decides when to run this test. It's just going to do it. Okay, so that takes a little bit getting used to figure out how it's kind of plumbing together. In PyTest, we can just use simple asserts. And then unlike vanilla Python, it won't just raise an assertion error, it will give us a better error because it does some complicated Python magic where it's going to actually rewrite this assert to be more specific. Kind of off in the weeds, but basically you'll get intelligent error messages if one of these asserts fails. When we organize our tests, we can have a bunch of tests in the same file like this. But what I like to do, especially since add is in my module, if my module also has, say, subtract, multiply, and so on, I like to group these into a class like that. So we have all of our tests for one function in this class here. And then we might have another class called test subtract and so on. So just keeping the tests kind of organized and clean. So let's look at an example of how we might use PyTest to test NumPy's norm in the linear algebra module. So we have two tests here. The first one is going to just assert that for a random array, we want to make sure that all of the values from the norm of that array are positive. Okay, and I guess there's only one norm here because this is a 1D array, but we could also do this along different axes. Here, we're going to test that if we have a single, not a number or a nan in the array, that the norm should be a nan as well. Okay. How would we run this if we wanted to run these tests? Now that we've written them.
Type pytest file name.
Yeah, exactly. We could type the file name, or we could just type pytest, and if it's in the same directory or even a subdirectory, it will automatically discover it. And then it takes care of deciding when to run these. Good. So if we do that, it looks something like this. We found our test norm function, our test norm file here. And then these two dots represent distinct test cases. They're going to be little happy green dots if it passes, big fat red Fs if there's a failure. And then it can also be an E, and an E means there was an error setting the test up. We can subselect them, just like you mentioned. If we only wanted to run the test in this particular file, we type pytest test norm.py, and we can even subselect based on certain test cases that we want to run. So in this case, we're only going to run that test nan returns nan and skip the rest. This is very useful when you're debugging and there's a particular test that's failing. You don't want to keep running the whole test suite, especially if it takes a long time.
So if you're going to use pytest file name, does the file name need to start with test also?
It's a good question. I believe if you explicitly pass it a file, it will look in that file.
Okay.
Yeah, so only if you're not passing it a file, it won't automatically discover things that don't start with test. I could be wrong, but I think that's how it is. Okay, so back to this domain and approaches. What did our test norm use? What was the domain and the approach?
How is it again?
Yes,
Oh,
all the way back here.
no,
Oh, the test. Oh, okay. Yeah, let's go back to that. Too far. Okay, so the test was this.
The first one is an example, right?
Yeah.
Yeah.
And it's probably a unit test because we're just testing one function.
Yes.
Yep. Okay, so domain, unit, and approach example. Okay, so another helpful thing with pytest, if you want to test that a function raises an exception, which if you have a certain input that is not allowed, that's defined code behavior, so you should test it. This is how you do it. So we're going to have this context manager. We do the with keyword pytest raises. We tell it the type of error, and then optionally we can pass a substring that the error message should contain. So that way, if this raises a type error, but it doesn't have the substring unsupported operand type, then it would still fail the test.
Can you see that again?
Yeah, let me back up. Okay, so what we're doing is we're saying that our add function, remember, it doesn't really work with a string and an integer. So its defined behavior should be that it raises an exception. So how do we test that? So the idea here is that we're going to use the pytest raises function here. And this is actually something called a context manager, which I meant to cover a few weeks ago, but we didn't get to it. So we have this with block, pytest raises, and then inside of its scope, we're going to add the call that will actually raise that exception. And if it doesn't raise the exception, pytest is going to fail this test.
Okay. So, and the message needs to be the same as.
It doesn't need to be the same. The message is going to be a substring. So it can be a longer message, but it has to contain those letters.
Oh,
Yeah. Okay. Another useful thing that pytest can do for you is parameterization. So let's imagine that we're doing unit tests that are example based. We might have a bunch of inputs and a bunch of outputs that we know correspond to those inputs. So for example, here, this IO tuple, we have 1, 2, and when we add those together, it should be 3, 4, 5, that's wrong. It should be 9, not 6. And then A, B should be A and B if we're adding strings together, because in Python, it's going to concatenate strings when we add them. So what we do here is we do at pytest.mark parameterize, and then we tell it the argument names for our test function, and then the sequence that we want to use here. And so what this does is it will essentially run this test 3 times, and the corresponding values for A, B, and expected will be 0, 1, and 2 for the first case, 0, 1, and 2 for the second, and so on. So this can make it a lot more ergonomic to write a bunch of these example-based tests. If you had to write a separate test function for each, it would become a little bit too robust. Verbose, I mean. Okay, who has a question about this? Anna, do you have a question?
I'm confused about the expected part.
Okay. So here we tell it that the 3 values for the tuple are going to be A, B, and expected. And so up here we have A, B, and expected. It's just because they're the same length.
and does that order need to be the same as the order of the inputs?
Yes. Yeah, that's how it knows which value to substitute in for these variables.
Okay. So let's say we did 1, 3, and 2, right?
Yeah,
And then we wrote A expected and then B.
it would still work.
Those still work.
Yeah.
So it doesn't have to be exactly the same as. I guess it has to match the tuple, but it doesn't have to match like the function call.
Right. So yeah, again, for the first line of the tuple here, 1 would be substituted in as the value, the first value, 2 the second, and 3 the third value. You could switch the order, but then you'd want to switch the order of your keyword arguments as well. Okay, so this is a little bit of motivation to discuss why we need test fixtures and what fixtures are. So if we look at the anatomy of a test, the different parts we have in a range, which is where we set up the testing conditions or the state that we need to perform our test. We have an act where we're going to perform some behavior that we're testing. Again, we're measuring the divergence or the difference between our expected plane and our actual code behavior plane, like we talked about earlier. And then we have assert. So we're going to test something about the behavior and formalize it with an assert statement. And then the last step might be some cleanup. So let's break out one of our tests very explicitly here into these 3 components. So the first would be our arrange or our test setup. So to set up our test, we're going to define 2 values here. The act is going to be the step where we actually perform the behavior. So in this case, we're going to store the output of our add function in this out variable. And then we have an assert. And here we're just asserting that the addition is correct. And then at the end, we might have some tear down. Now, of course, this is silly. We don't really need to delete these variables because they'll delete themselves when they go out of scope. But if this was some test that involved a database, for example, we might want to roll back a transaction or delete a temporary file, whatever it is, there can be some tear down after our test. And it's important that the tear down runs regardless of whether or not the test failed or passed. In this case, that wouldn't work, right? So we have all these 4 components in one test, and it has no way of knowing which part of it is the test and which part of it is really the setup and the tear down. So the solution for this that pytest provides is something called fixtures. And this isn't unique to PyTest. There's other testing frameworks in different languages that use this concept as well. But basically, they help us manage the arrange and cleanup steps. Sometimes they even perform the act step, but they won't perform the assert step. That should be left exclusively to the tests themselves. What they do is they inject the objects that are under test into the test function. I'll show you what that means in a moment here. And then we can control the scope, how often these fixtures get run with a scope keyword. And then, as I mentioned, the tests let pytest know which fixtures it needs by its naming of its keyword arguments. So let's, and there's many built-in examples of fixtures that are useful. For example, if you wanted pytest to automatically create a temporary file for you, temporary directory, you can just use this temp path. If you want to capture the system, the standard error, standard input, that capsys will do that for you. So if you're testing that your function prints something, there's nice fixtures built in to help you do that. Okay, so let's look at what a fixture actually is. Here is our fixture. What we're doing is we're setting up an array with nans so that we can test our linear algebra norm on this array. And so we have a function. It doesn't start with test. It actually doesn't matter in this case though, because we mark it with this decorator at pytest.fixture. And then inside the fixture, we're going to set up our array here. So this is the arrange. And then what we do is we yield a value out. So this is different than return. This is yield. Has everyone seen yield before? No. Okay. Yeah, they're
It's used for generator.
exactly. Yeah. Whenever you see yield, you should think that the function, rather than destroying all of its memory when it returns, it's actually saving its state, and then you can resume that function later. So yield random, that is going to let us know that in this test nan returns nan, because this parameter name here is array with nans, pytest knows that it needs the value from this fixture. See, the fixture name and this parameter name are the same. So when we run pytest, when we interact with this function here, array with nans is actually going to be the output of the fixture. So in this case, we have our random array with one nan in it. Any questions on that? This kind of looks like magic when you first see it, but it's pretty simple once you get used to it. Yeah.
So it wouldn't work if you just, instead of using yield, did return random and then go into the next function. If we could have the delete.
Yeah, exactly. Yeah. We could use a return there if we didn't have any cleanup.
Yeah.
I'm showing yield here because you might have cleanup for after the test runs. Yeah. Okay, so the next thing that's going to happen is we're going to do our act step and then our assert step, which are here and here. And then finally, when the test is over, this fixture is going to resume running and it's going to run line number 9. Okay. Okay, so fixtures are controlled by the scope keyword. So how often they get run. Ideally, you'd want to run a fixture every single time you have another test to make sure that there's no contamination between state. Like if you, in this, I'll show you an example here. It's not this one. In a few slides where we have a list that gets returned from a fixture. Well, the problem is some of the tests might change the list. And then the next test that uses it, if the fixture doesn't run over again, it will get that list that's been changed. So we have issues with mutable state at times. But what can happen is these test setup can be really expensive. So maybe we don't really want to run them every time. We're just going to be careful that we're not changing the output values, knowing that they'll get reused by other tests. So in this case, we're saying scope equals class. And so for every test class, we want to run this fixture once and then give the same value to each of its tests. If we said scope equals function, then it would be run again every time a function requests the fixture. Is that clear? Yes. So scope equals class. Well, basically, remember we talked about how this yield statement is going to return some value. Okay. what the scope equals class is going to do is it's going to say for each test class, so a class that has test cases in it, we're only going to run this once, and then each of its tests will get the same value in succession. And then we'll run the cleanup when the whole class is done running.
So all the functions in the class will have like same value of random to test.
Exactly.
And then it will clean the random once all the tests.
Once all the tests in the class are run. Yep. We can also use function scope. We can use session scope. We can use module scope. Those are the scopes that are available to us. So let's talk about it a little bit more. Knowledge check. What's wrong with this test? This is a really common mistake. I've probably done it hundreds of times.
Return.
No, so return is okay as long as we don't have a cleanup step.
Test data one should take data as an.
Exactly. We haven't formally requested the output of that fixture for this test. Even though we're using it down there, that data is actually just going to be the function. Okay, what about this one? So we have two tests. We have a fixture that has a session scope, so it's only going to be run once every time we run our entire test suite. You can see it's returning a list.
Yeah, so in test data one, we are changing the first value to 10. And then we are testing whether it sums up to 6.
Exactly. Yeah, you got it.
So just to check, this is definition because it's mutable, right?
Yeah. Yep. Two things we could change here. We could either use a tuple that we can't mutate, and then we can't do this, or we could use scope equals function, and then it will run every time a function test asks for it. So we'll get a new data for each test. Okay, so pytest marks. Marks allow you to organize your tests into kind of logical units. You define all the marks in pytest.ne. I'm not going to go into all the configuration and stuff. You can read about that on the pytest tutorial page. It's quite good. But the important thing is you might say some marks, some class of tests are maybe unit tests. Maybe you want to mark them as unit tests, or because you have more unit tests, maybe you just mark your end-to-end tests, and then you can control when those are run. Maybe you don't want to run them every time, just once in a while. That would be one example. Marks can also control if tests are skipped or expected to fail, and they control parameterization like we saw earlier. So let's look at a few examples. Here's a mark that marks this as slow. So if we're going to test making new friends and you're a guy in your 30s, it just takes a long time. So we don't want to run it every time. We can skip it for a reason, like gazing into the abyss, right? The abyss gazes into you. So don't run that test. It's not safe. In reality, you might mark a test as skipped if you're not done writing the test yet. You don't want it to fail the test suite because it's a work in progress. Skip if. So if the first thing is truthy or it evaluates to true, then we don't run it. Windows is fine. I'm just being silly here. But it is common to say if you're on one operating system, run this test. If you're on a different operating system, run that test.
So is this on Windows?
That would be something you have to define somewhere else.
Oh, okay.
Yeah, it's not built in. Yep. And then expected fail. Impress my father. It's just not going to happen. So we never expect this test to pass. If you want to apply these tests to a whole module, you use this pytest mark at the top of the module, and now everything in that file will have that same mark. You can also apply marks to an entire class. So we do the same thing at decorator mark web test on this test download. So that would mark all the tests saying that they need some kind of internet connection or whatever you define web test to mean. And then if we wanted to run our slow tests, we just can use the -m flag in pytest. So -m slow, that says run the tests that are marked as slow. We can also run the slow tests, but not the web tests like this. We just need quotes, so slow, not web tests. Pretty intuitive how you select different marks like that. The main thing is just to have that -m flag and then something afterwards. So there's a few other ways to skip functions. If you find out during your test that actually there's no way this can pass now, but I don't want to fail it because there might be something wrong with the setup. Maybe we don't have a library installed or something. Then you can just call pytest.skip, and then the test gets reported as skipped rather than failed. Here's another example, just like I was describing. So import skip. So if you don't have the NumPy module at this point, it's just gonna skip the test. So that's a good way to test conditional requirements or optional requirements. Okay, any questions at that point? And then I'm going to go into just some tips for organizing tests and then some tips for working with PyTest, and then we'll be done. Yeah.
So is there any kind of best practices as far as when you choose for something to be a skip versus a fail? Like if somebody doesn't have NumPy and a huge section of the package will just not work. Are there any, is this risky?
Yeah, I think it would be, it's obviously up to the test writer, but if you had optional dependencies, for example, maybe your plotting is all optional, so you do this for matplotlib, you wouldn't really want to fail the tests because they probably know they don't have matplotlib installed. But yeah, kind of up to you. Okay, so really quick, some organization tips. So organize your tests into classes. And then use fixtures when an arrange step or a setup step is more than about 3 lines long. If other tests need that same setup, then you don't want to be duplicating that code. So that's another reason to break it into a fixture. Or if you need some kind of cleanup step, that doesn't belong in a test function, it belongs in a fixture function. So keep your fixtures as close to the test as possible and move them up as more tests need them. That way it makes it easier when you're looking through the code to find out where the fixtures are that they're requesting. And so they move from classes to modules, and then finally to this conf-test.py file, which is kind of like a global file you can put fixtures in for all of your tests. Okay, then when you organize your project, you have, say, x.py, you should have a corresponding file called testx.py. So the testing structure typically should mirror the project structure. All right, so here's an example. We have our fixture. So in this case, lines 5 and lines 9 are doing the same setup. So we're going to move that to a fixture, and then they just request that array. And then if we have more classes later on, further down in this test file, for example, testing 2 here that needs that same fixture, we'll move it up to the top of the file. Okay, so tips and tricks. A really useful flag is the PDB flag. So whenever you have a test fail, it's going to drop you into an interactive debugging session, and you can figure out what's going right there. There's a way to test coverage. That is how much of your test is actually run by your, how much of your code is actually run by your test suite. That's quite useful to know. Testing requirements are different for packages versus libraries versus scripts. We talked about that. PyTest also has integration with a lot of the IDEs, VS Code, PyCharm, for example, so it makes it quite easy to work with. And then when you do get in the habit of writing tests for your functions in your code, the consequence is that you start writing smaller, more modular, more testable pieces of code. So even though the tests are good in themselves, they have this pleasant side effect as well. And of course, the last thing is to have fun. Okay, so I was going to do a demo here, but we're out of time. So I would strongly encourage anyone working on DAS Day to go through these exercises. I've kind of written them with that in mind. Okay, so any questions? Okay. Hopefully you all get a chance to play around with PyTest or testing in whatever form.
Thank you.
Yep.